The Standard Model of particle physics is the most rigorously tested framework in science, yet it contains a glaring omission. It relies on 19 measured free parameters, particle masses and coupling strengths, that cannot be derived from first principles. They must be observed and manually plugged into the equations. To understand why the theory hits this wall, we have to look at the mathematical foundation of spacetime itself, the Minkowski metric. This equation defines distances in a four-dimensional universe. But if you look closely, you will see one specific algebraic anomaly. The spatial coordinates are positive, while the time component has a leading minus sign. Standard physics treats this minus sign as a bookkeeping convention, a way to mathematically separate time from the three dimensions of space. But in the physics of strings and waves, a relative minus sign between derivatives is the explicit algebraic signature of physical tension. It represents a substrate that pulls back when displaced. If we apply that definition here, time is a one-dimensional physical substrate under extreme tension. Space is what we perceive when that time string is deflected transversely. Shifting our view of time from a passive coordinate to a tensioned physical string provides the first mechanical explanation for the geometric origin of mass. When you treat time as a tension string, those 19 arbitrary parameters of the Standard Model stop being arbitrary. They become predictable. This is a mass table for 54 different baryons and pentaquarks. Every value here is derived entirely from the geometry of that tension string. The free parameters count is 0. There was no curve fitting, no hand-tuning of individual masses, and no coupling constants imported from external experiments. Across the entire spectrum, from light protons to heavy bottom quark baryons, the mean absolute percentage error is 0.2498. The predictions and the experimental measurements are nearly identical. Mathematically, any attempt to fit 54 data points using 0 variables should result in an exploding error rate. Here, the accuracy holds. We can trace this exact mass data back through the geometry, beginning with that minus sign in the Minkowski metric. This zero-parameter derivation suggests that particle masses are not arbitrary values we have to measure, but geometrically inevitable structures. We start with that one-dimensional time string, pulled taut under a tension equal to the speed of light. When energy interacts with this string, it applies a transverse load, forcing the string to displace. Under uniform tension, a displaced string is mathematically restricted to a parabolic curve. It's the same shape a suspension bridge cable makes under load. Because particles are stable, they must be modeled as closed wave-following loops. We must wrap this parabolic deflection around a circular boundary. Wrapping a parabola around a circle causes the wave to overlap with itself, creating complex interference patterns. A circle acts as a prime number filter. A prime winding, like 7 steps, closes exactly because it has no internal factors to cause a clash. But composite numbers, like 6, contain internal factors like 2 and 3. These factors create many resonances that clash and interfere with the main loop before it can stabilize. Stable matter can only exist in the specific winding modes that survive this destructive interference. To find the surviving modes, we must identify the symmetry requirements of the known forces. The strong force operates on 3 color charges, requiring a cyclic group of 3, or Z3.
Fermions possess 2 spin states, requiring a Z2 subgroup. Finally, the electroweak sector, which unifies light with the weak nuclear force, is governed by 5 distinct symmetry components, visible in the specific mass ratios of the W and Z bosons. This requires a Z5 subgroup. To contain all 3 symmetries in a single unified lattice, we multiply these requirements together. 2 times 3 times 5 equals 30. This is the minimum primordial, the smallest possible geometric base that can host the Standard Model's forces. Any geometric origin of particle physics is mathematically forced to operate on a mod 30 lattice. Now we apply our prime number interference filter to this 30-lane lattice. We use the Euler-Toscan function to identify the lanes that share no common factors with 30, the lanes that are coprime. Out of 30 possible paths, exactly 8 winding lanes survive the destructive interference. These 8 surviving lanes correspond exactly to the 8 gluons that carry the strong force. Each lane has a survival amplitude, a projection weight, defined as the sine squared of the lane number times pi over 15. This geometric formula is algebraically identical to the Lushar-Weiss correction used in lattice QCD. For 40 years, physicists have used this specific formula to make supercomputer simulations match real-world experiments. They used it as a numerical patch, but it is actually the fundamental geometric interference pattern of a tension string. We can now translate these 8 geometric lanes back into the physical masses shown at the start. In this framework, mass is not an inherent field property, it is a projection amplitude. A particle's mass is simply its winding path projecting onto the time string. Particles in high projection lanes are heavy, while those in low projection lanes are light. To find the total energy density of the system, we sum the projection weights of all 8 surviving lanes. The sum of these 8 lanes is exactly 7/2. In quantum physics, the beta function tracks how the vacuum polarizes around a force, essentially how much the empty substrate weights the force carriers. Our geometric sum of 7/2 is the value of that vacuum weighting. When we plug this 7/2 geometric sum into the beta function and solve for the number of quark flavors, the result is exactly 6. All 6 quark flavors, including the heavy third generation, are required by the geometry of the Mod 30 lattice. To ensure this isn't just a subatomic coincidence, we must scale the geometry up to the macroscopic extreme, black holes. We apply the same projection weights to the interior geometry of a collapsing star. While relativity predicts a featureless singularity, this geometry replaces it with 4 distinct inner collapse shells. These shells form at precise radii determined in the same geometric weights that give quarks their masses. Because the underlying geometry is Mobius twisted, it assigns opposite winding directions to the north and south poles of a rotating black hole. This creates a physical consequence, a 6.667% differential in the precession rates at the 2 poles. This is a concrete, testable prediction. If telescope arrays like those observing M87 find that the north and south precession rates are perfectly identical, this geometric framework is falsified. The Standard Model treats the properties of our universe as a list of arbitrary measurements. This framework suggests they are the rigid, predictable results of a single tensioned geometry.